instead of the n, you have a 3n, because n particle and 3 dimensions. So I can use this equation. So it will be 2p3n over 2 gamma 3n over 2 radical 8m. Can I remove the radical and combine the exponent? 8m v 2 power 3 e h square 3n over 2. And this is the omega, what I told you. This is the omega. You have many appearance of the n. So n appear here several in the gamma, in the exponent, and here inside the radical and something. What's important for me is that this equation is proportional to the, look at that, proportional to what? We n e 3n over 2 and some constant of the n. And look at that, that was my expectation before I do the calculation. I told you that, you remember the example that I told you that you have an n particle and each particle can occupy the volume v, and we ignored the size of the particle, so the possible state was proportional to the v, and even before the calculation. But we find that by the integration. So what's the entropy? So entropy will be S will be called B and N omega. So you can replace that here. So you will have a lot of N here. So you have something. I don't want to write that. I want just to focus on the this term. Vn E3n over 2. So entropy will be some terms from the N. I will ask you in the homework to use exactly this and to do that. So that's okay. Now we can use the thermodynamic. For example, the first thermodynamic is that 1 over kBt, the equation is T, this equation, one of the famous. So you can take the derivative if volume and n remain the constant. Take the derivative of this equation. 1 over kBt will be from the s from the e, sorry, partial derivative of respect to e. So it will be 3 over 2 kb, and that will be 1 over t just. Sorry. Yes, 1. 3 over 2 kb n over e. And look what we can find from here is that e is 3 over 2 n kbt. You need to remember this equation from the fundamental of physics. Or thermodynamic energy. So it comes from here actually, it comes from here. Also the ideal gas PV n per T you can find from here. So my task was, I want just to show that how to find this omega. One thing remain here, the remaining things is that actually n is very big. So I want to again mention that there is no difference between n or 3n or something, because n is in the level of the Avogadro number. But you remember my case, the two-dimensional case. So it seems that the real omega is something related to the area, yes? It's related to the area, not to the volume. But as I mentioned before, at the large number of the particle, there is no difference between the area and the volume. Anyway, but there is some difference, but not very change. So actually there is a difference between V3n and the S3n, but ignorable actually when n is very big. if somebody want to use exactly the area, do you know what you will do? Is that you need to write the relation between the area and the volume. They are actually different. Their difference is actually coded in the change in the energy. So you have a surface here, so this is the S2, and that's the V3 cubic volume. I want to make a statement that the change between the volume and the area comes from a change in the band of the energy. I mean, you have the idea of how to calculate the volume. So the volume was the difference, the radius difference between two very infinitesimal volume multiplied to ds. V was, remember, S dr.
Yes.
Several times I write. This dr can be translated, if you want to talk about the energy, translated to this fact that you needed to keep the energy in the very narrow band.
Yes.
So I want to tell you, so you understand how to find the S, or dr will be translated to the difference between this layer of the energy. And if somebody really wanted that S, so I think the best strategy is that to take the derivative from the volume with respect to the energy, because this is multiplied to the change of the energy, delta E. What is the delta E? Delta E is the change of this. This is the change of the band. But this is really not important here, I told you, because you will get, even if you take the derivative of that, the volume. But it's difficult to get the, but you can take the derivative, because from the n you have this is the dependent of the volume to the E. Taking derivative with respect to E just produce for you 1, 3, 2 over 2n more. And you have a lot of n you have here, so it will be observed here. So don't be worried. So I want to tell you that KB ln V 3n, when n is very large, so it's not, it's actually K ln that's a 3n. Even if I know that they are different, run the V partial derivative of the E multiplied to delta. Even if I know that. So either that, either volume or either the surface you can use to define the volume. But you use the volume. So the only problem, and you can derive all the thermodynamic equation from this entropy, from the S, Kb, ln E. Just there is a one, so let me to write one time this, Kb, ln, the whole of that, ln 2 pi 3n over 2 gamma 3n over 2 multiplied to some constant am h squared 3n over 2 vn multiplied to e 3n over 2. Okay, some of the logarithms are very straightforward to take. So KB